So chapter 8 is about main memory, okay, and we know about the importance of main memory. We know that if any computer system does not have main memory, then you cannot run programs, because if you have a program in the hard disk and you want to run it in the CPU, then this program must be first brought into the main memory to make a process, and then the CPU executes the instructions of the process from the main memory. This is the importance of main memory. Now for a CPU, it can only access registers and main memory. Now for main memory, it has only the information about addresses. Main memory only knows that it has a set of addresses, okay, that starts from 0 until the size of the memory, okay, and whenever CPU requests to read something from main memory, it will give the read request and the addresses from which to read. Or if the CPU wants to write something into the memory, okay, saving some data into main memory because the user makes some changes, then the CPU will set the addresses. It will send those addresses to the memory unit in which to write, and it will also send the data to be written into those addresses. Now one issue is that if the CPU accesses data from the register, then it can be done in one CPU clock. But if the data is to be accessed in main memory, then it can take many cycles. And this time taken for many cycles is actually known as a term which is called stall, memory stall. To reduce the memory stall, what we do normally is that if we have CPU, okay, let me draw this for you. If we have CPU, okay, this is my CPU, and this CPU is on a chip, okay, and there are registers in the same chip, okay, these are different registers, and there is RAM. The CPU wants data from the RAM. So for a program execution, if let's say this is a process in the RAM, then to execute the process, its data will come from the RAM, its data or instruction will come from the RAM into the registers, to any register, okay, and it will be executed in the register. So CPU will actually directly access the instruction from the register. And as I explained, if it is going to get the data from the main memory, it will take some time, resulting in a stall. To actually reduce that, what we have is that between the CPU and the memory, we have something what we call as cache. Okay, so cache memory. Why is cache memory useful? Because the cache, so we have this cache. I cannot write it here somehow. Cache, C-A-C-H-E. Okay, now this cache memory, it will get the data from the RAM, okay, and then because it will get many instructions at the same time, so one by one all these instructions will come into the CPU. Now this access from CPU to the cache is fast as compared to the access from CPU to memory, which is quite slow. So that's why cache is useful. Now, because in the RAM there can be many programs at the same time, so this one is one program or process, then we can have another process, and we can have yet another process in the RAM. Okay, so these different processes, they belong to different programs, and we do not want that any process can access the address of another process, because this can lead to security problem. We don't want this security problem to happen, so we want memory protection. We want that a process can or should only access its own addresses and not any address outside its area. So for example, here we see that in this RAM we have three processes. Okay, each process has its own address area, okay, which is denoted by what you can see, these address numbers. So for example, the operating system is in the addresses which start from 0 to 256,000. In this memory area you have the operating system. Then you have another process, let's call it process A, for example. So this process A, it has the address from 256,000 to 30040. This total area, okay, is actually the address of this process, okay, and this process is here. Now what we have is that the CPU must be executing instructions of process A which are only within this range, which are only from 256,000 to 30040. Okay. Similarly, for process B, the CPU must execute only those instructions which are in the range of this 30040 until 1209000. Okay, this is for process B. So how does the CPU know about them? For this purpose, the CPU has something which is called the base register and the the limit register. Okay, so the base register and the limit registers, they have the value of those areas within which this process is residing in the RAM. So here you see that process B is between these limits of base and the limit register. Now whenever the CPU wants to make a reference for process B, it will make sure that it is more than the base and less than the limit. So on the left side of the RAM, what you see is actually the memory addresses, and on the right side, the base and the limit, these are the registers. So the base address here is same as the address on the left, 300,040, but the limit is different for the address and the limit register. Why is it that? Can anyone tell me? Actually, the reason is if you add the base number, okay, and the limit, so together they will give you the same number, which is 420,940, which is this number on the left. So it means that this limit actually represents the size of the process in the RAM. So the size of this process is 120,900. Every time the CPU wants to have an instruction from process B, it will be within these addresses from 300040 to 120900. How does a CPU do that? Actually, this is done by a hardware address protection unit of the memory, and what happens is that when a CPU generates an address for a process, we are going to verify two things. The first thing is whether this address is greater than or equal to the base address, because for process B we know that its address must be greater than the base address of 300040. If it is less than the base address, then we will not allow the process B instruction, because it may be from process A or from the operating system. It will not be inside process B. Similarly, if it is greater than the base address, then the next check is to check if this is less than base plus limit, which means that we will make sure it is not in the next process or some other part of the memory, it falls within process B. That is actually, if true, then we will get the access to the memory area or the memory address. If it is false, then we will trap to operating system monitor, and this will result in the addressing error. So having an address less than the base address or more than the base plus limit address will result in the protection error, which will be generated to the operating system, and the operating system will give the error to the user, and it will stop executing the process. So how does this addressing scheme work in general? Because we know that when we write a program, we write some code, we compile the program, it is stored as an executable file, and when you run the executable file, this program is converted into process into main memory, and then the CPU executes the process from the main memory instruction by instruction. This is true for one program, as well as you consider the case when you have many programs. So you load many programs into RAM at the same time. Whenever you want to load different programs into the RAM, they will go through the input queue, the queue of all those programs which are going into the RAM. So the input queue will contain many processes at the same time. Now, if we consider a single tasking operating system in which there is only one process executed at the same time, then we know that we can load the process as some starting address, for example 000, and that program is executed from the started address. When the program finishes, we load another program into the same address starting from 000. But we know that modern operating systems, they are not single tasking. Rather, in multitasking operating systems, many processes, they are executed at the same time. So what do we need is the ability to load a process anywhere in the main memory, and this requires the ability to actually manage these addresses of the processes at runtime when the process is loaded. Now normally we deal with three types of addresses depending upon the different stages of a program's life. So the first part in the program's life is about the source code when a user writes a program. And in source code, you know about C, C++ or Java programming, you never know the addresses of your instructions or variables. Actually, what is important to you is the name of the variables that you are using in your program. So for example, if there is some value in memory you don't remember the address of the memory, but you give a name to that memory location, and this name is known as a variable. Then using the name of the variable, actually you can access that address. For example, if variable a is equal to 5, so it means that a is some memory location which contains the value of 5. So these are known as symbolic addresses using variable names. Then the second type of addresses is known as relocatable addresses. Relocatable addresses are actually something which depend actually on the loading of the program. Where do you load it in the memory? So it will always we store in a relocatable code, we refer to an address starting from some starting address. For example, the very first address in a program is 0. Then in a relocatable code, we will say that this instruction is located 14 bytes from beginning, or this instruction is located 100 bytes from the start of the program. This is relocatable. Why is relocatable address needed? Because when you run the program, it is loaded into memory. It does not know where is this in the memory, but it will always refer to the start of the program as the starting address, and the next instruction will depend on the starting value of the address. This is the compiled code. Then the linker or the loader, it will bind the relocatable address to absolute addresses. For example, the actual program can be loaded into memory location 74000. So the relocatable code at 14 bytes will be at the address of 74014. It is 14 bytes from the starting address, which is 74000. Okay, so here I will write just for information that this one is actually will be the result of 74000 and then 14 bytes from start. Okay, so it will give you this effect of 74014, and this conversion of address from, let's say, relocatable to absolute addresses, this is known as address binding. So we have different types of binding. One binding is from variable name to relocatable address, and the other one is from relocatable addresses to the physical addresses. And this binding is both for instructions and data. In a program, you can have instructions, for example, print or cin, etc. These are the program codes. Or it can be about data, which is the variables of the program. Now this binding of instructions and data can happen at 3 different times. The first it can happen is at the compile time, which means that if memory location is known in advance, then you can generate absolute code. So let's say we know that a program will be executed at address number 100. It will be loaded started from address 100. Then we can have an absolute code in which we write, let's start the program from address 100. But actually it does not work like this, because you are not sure at the compile time that what will be your address of execution. So the next thing is to have actually these addresses bound at the load time. This binding takes place at the load time when you load the program into the RAM. And in that case, we must have the relocatable code, which means that we don't know about the starting address, okay, in which this program will be loaded, but we will generate a code with respect to any starting position. So this program can be anywhere, and we will know that wherever this program is, I will refer to an instruction with respect to the starting position of the program. Then the third thing is about execution time, which means that the binding is delayed until the runtime if the process can be moved during execution from one memory segment to another memory segment. And this is what is happening in the modern operating system, that your program can be moved in different locations in memory when it is executed. And for this to happen, the execution time binding, we need support from hardware for mapping of these addresses. And this is done in the example of base and limit registers that I explained before. So this diagram represents the whole schemes, that if we have a source program and we are considering compile time binding, then this address binding is done at the level of compiler or assembler, and this will result in an object module which will have fixed binding. Similarly, in the linkage editor, it links actually your object modules to other object modules, which means that within your program you write your own code that will be your object module, but your code will include some other object modules from the programming language. This linkage is done and you load the module, okay. So all this processing is done at the load time. Now the loader is an entity which will actually combine the load module with the system library by the operating system, and in the memory you will have the image of the program. But during the runtime or the execution time, this program image, it will need access to dynamic linking file through dynamically loaded system library. An example is the DLL file. Now a DLL file is present in the operating system, and when a program needs services, they load from the DLL file. And these DLL files are normally available at different locations in the operating system and used by the programs. So now we need to distinguish between two types of address spaces. One is known as the logical address space, the other one is known as the physical address space. So a logical address space is different for each process, while a physical address space is same for the whole system. Why is it different for each process? Because a logical address space means that when you load a process into RAM, so for that process, because it only knows its own addresses, for it the starting address is always 0 and the ending address is the limit of that process. That is the logical address space. And the other one is physical address space, which is actually the address space seen by the memory unit, which consists of the RAM in the system. So what CPU does is actually generates the logical address space inside each process. So it will say that execute instruction number 5 in this process, or execute instruction number, for example, 50 in this process. So it will send the address of the instruction in this process to the memory unit, and this will be known as the virtual address or the logical address. Now the memory unit will take this virtual or logical address and it will convert it into a physical address which will be in the RAM. Then the data or the instruction at that physical address will be fetched from the RAM and loaded into the memory. So logical and physical addresses are the same in compile time or load time address binding schemes. But in the execution time address binding scheme, they are different. Logical address is different and physical address is different. So the logical address space is actually set of all logical addresses generated by the program, which is limited by its size, starting from address 0. And the physical address space is a set of all physical addresses generated by a program. If we don't consider virtual memory, then this is the random access memory, the size of the random access memory in which this program can be placed anywhere in the RAM. Now we should understand the role of the memory management unit. What is a memory management unit? It is a hardware device that maps the virtual memory address to physical memory address at runtime. And there are different methods to map this virtual address into a physical address, and we will see those schemes in the rest of this chapter. So for example, we consider a simple scheme where we have the value in the relocation register, which is the starting address of a process, and then we add the value of the relocation address to every address generated by the CPU, because the CPU will generate a logical address, and to get the physical address we will add the logical address with the relocation address value, and then the final value will be some physical address in the main memory. Now this is known as the relocation address. We don't call it a base register now, we call it as the relocation register, because it will give us the addresses according to the position of the process in memory. So if we consider MS-DOS operating system, then it would use 4 relocation addresses. Now modern operating systems, they use different number of relocation registers. So for a user program, it only knows about its own addresses, and these are the virtual or logical addresses, which always start from the first instruction, which is at position 0, and it goes until the size of the program. For a process, there is nothing more than its own addresses. It does not know anything about other processes in the RAM or the size of the RAM, etc. It only has its own world in terms of its own addresses in the main memory. So in execution time binding, when the CPU makes a reference to a memory location, then this binding occurs, which means that at that time a translation is made from the logical address to physical address. In this way, the logical addresses, they are bound to physical addresses. Now here we see the example of dynamic relocation using a relocation address. So the relocation address, it contains the starting address of a process in the relocation register. So within the logical address of a process may be executing the instruction number 346. So the CPU sends the logical address of 346 to the memory management unit. The memory management unit will take the logical address and will add it to the relocation address to give us the physical address in memory where we can get this from. So all this mapping from logical address to physical address is done by the memory management unit, which is hardware, and it does not require any special support from the operating system. The operating system can help in the dynamic loading of the program into different areas of the memory. Once a process is in memory, then the job of the memory unit is to translate the logical address of that process into the physical address. Now we have the concept of dynamic linking and static linking. What is static linking? Static linking means that the system libraries and the program code which is written by user, they are combined by the loader into the binary program image. So the system libraries become part of the binary program. When you load the program, the system libraries are loaded inside the program. There is no need to call additional libraries from the program because they are inside the program. This is the concept of static linking. In the dynamic linking, the system libraries are not linked with the main program, and this linking is done at the time of execution. Now there is a small piece of code which is called Stub, and this is used to locate the appropriate memory resident library routine. Its job is to find where can it find this system libraries. It contains the information about system libraries, or it can communicate with the operating system to get to the libraries. Now when you run the program, so initially the stuff is there inside the main memory, but once there is a need to execute the system libraries, so the stuff will replace itself with the address of the routines in the system library. A routine is actually a small part of a program. Now the operating system will check if the routine which is needed by the process, it is there in the process's memory address space already, then it will run the routine from there. If it is not in the address space, then it will add the routine to the address space. So the dynamic linking is very useful for libraries. It is used quite significantly in the Windows operating system in the form of dynamic linked libraries file or the DLL file. These DLL files are also known as the shared libraries because they are shared between different processes. So they are present in the operating system. When you load any program and they need these libraries, a reference is made to the library by the program, and the library is included in the program for use by this program. So we stop here, and then next time we will start with swapping. If you have any question, you can ask me.